Welcome to the second lecture of Arenes. Let's recap on what we covered in lecture 1. We went through the structure and properties of benzene. As for the reactions, we learned about nitration, halogenation, and Friedel-Crafts alkylation. All of these reactions proceed via electrophilic substitution mechanism. Moving on to the physical properties of methylbenzene. Methylbenzene is a monosubstituted benzene derivative. Like benzene, it is also a colorless liquid. Methylbenzene is nonpolar in nature and hence insoluble in water, but soluble in nonpolar solvents. As its fumes are considerably less toxic than those of benzene, methylbenzene is more preferred as an organic solvent. Recall the structures of benzene and methylbenzene shown on the bottom right-hand corner of the slide. Methylbenzene has a higher boiling point than benzene, as it has a greater number of electrons. This results in stronger ID-ID interactions between its molecules. On the other hand, methylbenzene has a lower melting point than benzene, as it is less symmetrical, leading to less efficient packing and less extensive ID-ID interactions. Reactions of methylbenzene. Now when we look at methylbenzene, we need to realize that there are two parts of benzene that behave quite differently. First, we have the side chain. Groups that stick out of the benzene ring are what we call side chain. The side chain can be long and complex, but in methylbenzene, it is just an alkane because there is no functional group for methyl. So just like an alkane, the side chain can undergo free radical substitution. Oxidation-wise will be slightly different because side chains of benzene undergo oxidation in a slightly different manner, which I will cover in just a bit. The benzene ring stays as a benzene ring, so it undergoes electrophilic substitution as supposedly so. However, now that it has a substituent, the side chain exerts a certain influence on the behavior of the benzene ring. We will discuss this in greater detail in subsequent slides. Alright, so let's focus on the methyl side chain reaction first. Because it is an alkane, it undergoes free radical substitution. The reagents and conditions are Cl2 gas, UV light at room temperature, and excess methylbenzene to achieve the monosubstituted product. The alternative to writing excess methylbenzene is to write limited Cl2 gas. The mechanism is free radical substitution, something that you are very familiar with. Please pause the video now and take 5 minutes to try drawing the FRS mechanism. Welcome back. Let us go through the mechanism. For a start, remember that it is compulsory to write the three headers: initiation, propagation, and termination. During initiation, a chlorine molecule absorbs energy in the form of UV light. This results in the Cl-Cl bond breaking homolytically to give two chlorine radicals. So I expect you to draw two half arrows starting from the Cl-Cl bond and ending on the Cl atoms. Next, during propagation, the chlorine radical removes a hydrogen atom from the methyl side chain of methylbenzene, forming the benzyl radical and HCl. Do take note that the dot representing the electron must be drawn on the carbon atom. The benzyl radical then abstracts a chlorine atom from a chlorine molecule, forming the monosubstituted chloromethylbenzene and the chlorine radical. This results in the regeneration of the chlorine radical. Finally, during termination, any two free radicals may combine to form a molecule. You will only need to show two possible termination steps, nothing more. The other side chain reaction of methylbenzene will be oxidation. Under acidic conditions, benzoic acid and water are formed. So to balance the equation, you will need to account for the oxygen that is added for oxidation. The square bracket O can be used to represent all the oxygen atoms that are supplied by the oxidizing agent. The reagents and conditions for this reaction are acidified KMnO4, heat. Sulfuric acid is used as the acidifying agent, as it does not lead to any side reactions with KMnO4. Observations. I trust you know your KMnO4 very well, which has an intense purple color. So when the oxidation reaction happens, the purple KMnO4 will turn colorless. When the reaction mixture is cooled, a white PPT of benzoic acid forms. This becomes a distinguishing test for methylbenzene, because not only does oxidation occur, but upon cooling, white PPT also appears, which is a clear sign that benzoic acid has been formed as a result. If you were to have the oxidation done under alkaline conditions, the benzoic acid that supposedly formed will further react with the alkaline medium. That is why you get a benzoic ion. Basically, it's the product when benzoic acid loses a H+. The reagents and conditions will be alkaline KMnO4, heat. Let's revise how this equation is balanced. First, we must recognize that benzoic ion is formed due to the alkaline conditions. Water is also formed. Next, we will balance the oxygen using square bracket O and reflect the alkaline conditions by incorporating an OH-. In order to balance this equation, you need to account for the hydrogen, and you must use the OH- that reacted with your benzoic acid. So the idea is that the benzoic acid formed further reacted with the OH- to form one H2O, whereas the other H2O was formed due to oxidation of the side chain. Two of the hydrogen from the methyl group need to be oxidized as well. What if we have ethylbenzene instead of methylbenzene? If it was ethyl, it means that there are two carbon atoms on the side chain. Upon oxidation, you will still get benzoic acid. So if you have a side chain that is subject to strong oxidation in acidic medium, you will always get benzoic acid as a product. But what happens to the rest of the fragment? In this case, after forming benzoic acid, you are only left with one more carbon. So logically, we expect one CO2 and water to form as well. Finally, you need to balance the number of square bracket oxygen. Observations for this reaction will be purple KMnO4 decolorizes. The white PPT of benzoic acid forms when the reaction mixture is cooled. But since CO2 gas is also being produced, you will expect formation of white PPT with lime water. Therefore, this becomes a distinguishing test between ethyl and methylbenzene. What happens if you have one phenyl propene? The side chain becomes more interesting as it contains an alkene functional group. Recall from the chapter of alkenes that the oxidation products depend on the number of alkyl groups bonded to each carbon end of the CC double bond. For example, a terminal alkene fragment will give CO2 and water upon oxidation. When one R group and one H is attached to the carbon of the CC double bond, we obtain a carboxylic acid. When two R groups are attached to the carbon of the CC double bond, we obtain a ketone. So for one phenyl propene, the left-hand side fragment will give benzoic acid, while the right-hand side fragment will give ethanoic acid. Remember to balance the equation using square bracket O to account for all the oxygen atoms that were used in the reaction. Please pause the video now and take 5 minutes to try checkpoint 2. Predict the product's form when one phenyl ethene is oxidized. Before you start, you probably should ensure that you draw the correct structure of one phenyl ethene. Welcome back. Let's check the answers together. When the CC double bond is cleaved, the left fragment will be oxidized into benzoic acid. The right fragment is a terminal alkene, which explains why CO2 and water are formed. You will also need to balance the equation by adding 5 square bracket O on the left-hand side. Alright, moving on, let's discuss about the substituent effects on the substituted benzenes. Earlier on, we talked about the side chain reactions, which include FRS and oxidation. Now we consider how the benzene part reacts, especially when the benzene has a substituent already attached to it. How do they behave differently when they undergo electrophilic substitution? First, Benzene has 6 hydrogen atoms, which have equal probability of being substituted because they are all the same. But the moment you have a substituent inside, you will generate a different probability of being substituted at a different position. The scientific explanation really is because the substituent, which is highlighted as a red S, has an influence on the electron density of the benzene ring, giving rise to some positions having higher electron density and some positions having lower electron density. Therefore, the substituent already on the benzene ring directs the incoming electrophile to a particular position with respect to itself. So first of all, we need to consider the impact on the reactivity of the aromatic ring. There are activating groups that make the benzene ring more electron-rich and therefore more reactive. So immediately you can imagine, right? It must be some electron-donating group, like alkyl group, OH, or NH2 group. You might be puzzled thinking how come OH and NH2 are electron-donating? Note that they are electron-donating only when bonded to a benzene ring. They are not electron-donating due to the oxygen or nitrogen. We will cover this in greater detail in the chapters of hydroxy compounds and nitrogen compounds. So now we need to understand, for an activating group, which is labeled as S here, for the substituent group, if it is able to enhance the electron density of the benzene ring, it makes the entire ring more susceptible to electrophilic attack. So it's basically making the electron-rich benzene more electron-rich for it to be more attractive to the electrophile. Thus, when you proceed with the electrophilic attack and form the uranium ion, you realize that the electron-donating S group contributes and spreads the electrons over to the uranium ion, which makes the ion more stable by stabilizing the positive charge. This causes the reaction to become more energetically favorable. Activating groups result in milder reaction conditions. For example, bromination of benzene requires a catalyst, but bromination of a phenol, OH being the activating group, will occur readily at room temperature without a catalyst. So you can see the activation energy is way lower, and it's easier for the reaction to proceed. If we were to have a deactivating group, it would make the benzene ring less electron-rich. So you can think of groups that are electron withdrawing, such as halogens, NO2, or COOH group. You might be a little confused by this point, wondering how do we memorize the substituent effects of different groups. The good news is there is no need to memorize because it's all printed for you in your data booklet. The table lists clearly which groups are ring activating and which are ring deactivating, so you just need to follow. The reaction conditions for benzene ring with deactivating groups will be harsher. So maybe in the original compound, we just need a catalyst, but now you will need to subject it to higher temperature as well. If you are keen, you may read further on the inductive effects and resonance effects that cause this particular situation. So what happens is that if the substituent is a deactivating group, it will decrease the electron density on the benzene ring, making it less susceptible to electrophilic attack. On hindsight, even as the reaction proceeds, you get a positively charged uranium ion. So it really doesn't help that the substituent is still trying to withdraw electrons away, which makes the uranium ion even more electron deficient and destabilized. This causes the reaction to become energetically less favorable. As a result, I will need an external source of energy to drive the reaction forward. Here is a picture to illustrate the electron density in the compounds. The bottom row actually provides a cross-sectional view so that you can see the bonding inside. Unfortunately, the diagrams generated by computational chemistry often look like donuts, so you cannot see the bonding clearly. I have tried to label the NH2, OH, CN, and NO2 groups regardless. So on the ball and stick diagram, there is a benzene with NH2, and this is a benzene with OH. You can see that when NH2 and OH is bonded to benzene, the red region takes on a slightly triangular shape, showing that electron density is intensified on positions 2 and 4, whereas the red region on benzene is quite evenly distributed, shown by the red circle. On the other hand, when you have a CN or NO2 bonded to benzene, you can see that the color deviates far from red, which means that the compound is not as attractive to electrophiles anymore. So all this can be done using computational chemistry to show the substituent effects on benzene. Such electrostatic potential maps for various substituted benzenes indicate the electron-rich positions on the ring, as well as the electron density of the benzene ring compared to unsubstituted benzene. Next, substituents that are present on the benzene ring will influence the electron density of different positions on the ring relative to the substituent, hence the position of the substitution of the incoming electrophile. The reactivity of the benzene ring towards the electrophile will also be affected by the substituent that is already attached to the ring. Beyond affecting the reactivity of the aromatic ring, it also impacts the site of attack, meaning where the incoming electrophile is going to land. For example, your original substituent is always taken to be at position 1. So if the substituent is stated as 2,4 directing in the data booklet, this means that the incoming electrophile can only land on position 2 or position 4. Position 2 is known as auto, while position 4 is known as para. If the substituent is 3 directing, then the incoming electrophile will only go to position 3, and this is called meta. So it's auto, para, and meta positions. The general guide is that saturated groups are 2,4 directing, while unsaturated groups are 3 directing. However, exceptions will apply. So the moral of the story is to refer to your data booklet to be sure. Alright, to help you better understand this concept, I'd like to use this analogy of a traffic controller at the airport. For example, I have an already substituted benzene ring. The already substituted group will act as the traffic controller. He is on the ground, so he will be directing the incoming electrophile, which I will represent with an aeroplane. The substituent that is already on position 1 of the benzene ring will give instructions. Let's say the instruction is incoming electrophile on position 3 only. Then the incoming electrophile has no choice but to be substituted on position 3. This is the table in Data Booklet section 8 that you are supposed to refer to. Make sure that you familiarize yourself with this page and the information provided. The final substituent effect is the number of substitutions. The nature of the substituent already present on a benzene ring determines the number of substitutions. Suppose if the substituent is very activating, then we might expect multiple substitutions to happen. We will learn this in greater detail in the chapter of hydroxy compounds. Now let us take 5 minutes to try checkpoint 3. What will be the final products formed when benzene is reacted first with a mixture of corn HNO3 and corn H2SO4, then with Br2 and AlBr3, as opposed to first with Br2 and AlBr3, then with a mixture of corn HNO3 and corn H2SO4. Clearly, checkpoint 3 is trying to check whether you understand the directing effects and whether you are able to place the respective groups in the correct position. To identify the intermediates and final products formed, you are recommended to present your answer in the format shown on the slide. Let us go through part A. When benzene is first reacted with corn HNO3 and corn H2SO4, nitrobenzene is formed. Note that the temperature must be maintained at 50 degrees Celsius. As the NO2 group is 3 directing, the second substitution occurs at position 3 of the ring, otherwise known as the meta position. Therefore, the final product formed is 3-bromo-nitrobenzene. Moving on to part B, When benzene is first reacted with Br2 and AlBr3, bromobenzene is formed. Since Br is 2,4 directing, the second substitution occurs at position 2 and 4 of the ring, otherwise known as auto and para positions. Take note that since Br is ring deactivating, a harsher reaction condition is needed in the form of a temperature higher than 50 degrees Celsius. At this juncture, you should learn to recognize that questions like checkpoint 3 belong to a category known as reaction scheme questions. In reaction scheme questions, the balance equation is not required, as reagents and conditions are written on the arrow itself. You should also be able to differentiate between the demands of reaction scheme questions and mechanism questions. Methylbenzene undergoes similar reactions to benzene, as the methyl group is ring activating due to its electron donating ability. Methylbenzene is more reactive than benzene. Therefore, the nitration of methylbenzene can be carried out at 30 degrees Celsius rather than 50 degrees Celsius as for benzene. Also, the methyl group is 2,4 directing. Let's see how this is illustrated in a reaction scheme. Nitration of methylbenzene can occur at 30 degrees Celsius due to the ring activating property of the methyl group. Furthermore, as the methyl group is 2,4 directing, the NO2 group is substituted at positions 2 and 4 of the ring. Likewise, during the halogenation of methylbenzene, the Br is being substituted on positions 2 and 4 of the ring. This is because the methyl group is 2,4 directing. Please pause the video now and take 5 minutes to try checkpoint 4. Suggest a method of synthesis to convert methylbenzene to 3-nitrobenzoic acid, stating the reagents and conditions required. When attempting this checkpoint, do consider the directing effects of the different substituents carefully. Let us go through checkpoint 4. You should have first performed an oxidation, followed by a nitration. When methylbenzene is heated with acidified TMNO4, we will obtain benzoic acid. As the COOH group is 3-directing, it will direct the NO2 to occupy position 3 of the ring. Also, since the COOH is ring deactivating, it explains why a harsher reaction condition is required in the form of a temperature higher than 50 degrees Celsius for nitration. Let's find out what happens if we reverse the sequence of steps. If we perform nitration first, we will realize that the NO2 is being substituted on positions 2 and 4 of the ring, giving rise to two products. This is because the methyl group is 2,4 directing, after which, during oxidation, the methyl group is oxidized into COOH. Whichever the case, we will not be able to obtain 3-nitrobenzoic acid. As we still have some lecture time, please take 5 minutes now to practice describing the mechanism of the reaction to convert benzoic acid to 3-nitrobenzoic acid. Let us go through the mechanism. In step 1, corn HNO3 reacts with corn H2SO4 to generate the NO2 plus electrophile. Step 2 involves the electrophilic attack of benzoic acid by NO2 plus. Thus, in your drawing, you must show an arrow that starts from the benzene ring and ends on the nitrogen atom of NO2 plus. A slow step occurs and the uranium ion is formed, bearing in mind that the NO2 plus is substituted at carbon 3. The positive charge should be delocalized over the 5 remaining carbon atoms. To restore aromaticity of benzene, the uranium ion loses a proton in the fast step. This is shown by drawing an arrow from the CH bond back into the benzene ring. 3-nitrobenzoic acid is formed as a product and the sulfuric acid catalyst is regenerated. So once again, what are the marking points? The first one is of course the equation for step 1. In step 2, I will be marking for the correct starting point of your arrow and the correct ending point of your arrow. The slow step, the correct structure of the uranium ion, where your arrow starts and ends, the fast step, as well as the regeneration of the catalyst. Last but not least, what are some common uses of aromatic compounds? We have methylbenzene that is used as solvent for your paint, which is why sometimes it smells. Also, it contributes to rubber, printing ink, adhesives, etc. Benzoic acid is used as a food preservative because it can inhibit the growth of mold, yeast, and some bacteria. It is also used as a constituent of the wheat fields ointment, which is used for the treatment of fungal skin disease such as ringworm and athlete's foot. What about naphthalene? It acts as a raw material in the manufacture of dyes and insecticides. If you browse through your TYS, you will notice that naphthalene often appears in challenging questions because it has two benzene rings and its properties make for very interesting question setting. Congratulations, this marks the end of Arenes. However, this also means that a new chapter on halogen derivatives is starting. So please tidy up and organize the information that you have gathered from this chapter before we move on. Organic chemistry is moving at quite a fast pace, and a lot of information is being loaded onto you. So do be consistent in revising what you have learned. If you have any further queries on this chapter, please feel free to post them on the lecture Q&A, and I will get back to you. Goodbye and thank you.